In this video, we'll be going over Hooke's law. So the formula you need to know is f of s is equal to negative k times x, where k is a spring constant, and the negative sign means that the spring pulls back towards equilibrium. Also, you need to know the formula for spring energy, which is PES is equal to, another notation to write that is potential energy of spring is equal to 1/2 k of x squared. So let's start with a question. Let's start with question 1. What is the elastic force a spring exerts if K is equal to 175 newtons over meters and it is stretched 30 centimeters? Now that's the solution, and now we're gonna double check this. We're going to verify this. So let's start with write our work for number 1. We have that K is going to be 175 newtons divided by meters, and it's stretched 30 centimeters. So let's write that down over here. X is equal to 30 centimeters, and we have to convert centimeters to meters. Every time you're working in physics, you always convert centimeters to meters because the SI unit for length is going to be meters. So let's see this. You have 1 meter is the equivalent. You should set up the ratio. You just multiply by this. 1 meter is equal to 100 centimeters. And yeah, so you just multiply. You get 0.30 meters. So let's plug that into the formula. F of s is equal to negative k of x, and this is going to be equal to negative 175 newtons over meters divided times 0.30 meters. So now you just type that into a calculator and you will get negative 52.5 newtons, and this is approximately going to be negative 53 newtons. Okay, great. So that's problem 1. Now let's move on to number 2. Number 2, it says, how far must a spring K is equal to 35 newtons over meters be pulled back in order to exert a force of 63 newtons? Now, let's write that out. So K again is equal to 35 newtons over meters, and we want F is equal to 63 newtons, and this is going to be F of S. So now we're going to use F of S is equal to K times X as the magnitude. So this is going to be the magnitude. So we already know what F of S is. So essentially, we're just going to rearrange to solve for the length. The length is going to be, this is going to be how far that you pull the spring back. So you want to solve for that. You simply just rearrange it with some simple algebra. You get X is equal to F divided by K, and then you just plug in your numbers. You get 63 newtons divided by 35 newtons divided by meters, and you get 1.8 meters. Great. So that is your distance. That's your x. That's how far the spring must be pulled back. Now let's move on to our next question. 3. What will the end length for a spring with rest length 82 centimeters and a spring constant of K is equal to 0.5 newtons over meters if it is stretched until it exerts 0.25 newtons? So let's write that down. So that's for question 3. What is so the final length when stretched until F is equal to 0.25 newtons is what we're trying to find. So we are given that we're given the rest length is going to be, we're just going to call this L initial. And L initial is going to be, was 82 centimeters. And converting centimeters into meters, you have this, you multiply by 1 meter divided by 100 centimeters, and then you get 0.82 meters. Now, we were also given that the spring constant K is going to be equal to 0.50 newtons over meters, and we were given that the force of the spring in its magnitude is going to be F is equal to 0.25 newtons. So we can rearrange this equation for the spring force here, and then we solving for x, we divide both sides by k, you get F over k, and then you just plug in your numbers again, simply 0.25 over 0.50, and you're left with 0.50 meters. Now, in order to find the new length, so this is going to be your new length, you're going to have to add your initial length plus the x that we just solved for, which was the distance that we stretched the spring. So this is the distance that we stretched the spring in order to produce a force or use a force of that magnitude with the spring constant, So we have that. That's the distance. So yeah, you're just gonna plug in what you got for x into here with your L initial. L initial was 0.82 meters, and you're gonna add 0.50 meters, and you're gonna get for your new length as 1.32 meters. Great. So let's do the next question. For what is the energy in a spring compressed? What is the energy in a spring compressed 5.0 centimeters with a spring constant K is equal to 500 newtons over meters? So let's work this out. We're solving for the energy in the spring, and the spring is compressed 5.0 centimeters, and our spring K constant is going to be K is equal to 500 newtons over meters. So let's say, so for our X, we want to convert this is going to be that's our X, is 5.0 centimeters. That always has to be converted into meters. So you're going to multiply that by 1 meter divided by 100 centimeters. And then centimeters cancels out, you just multiply across, that's just going to be 0.050 meters. Now, we're going to, for this equation, we're trying to find the energy in the spring. So, when you find energy, you have to use potential energy of the spring formula. So the potential energy of a spring is going to equal to, again, our formula was PES, potential energy of the spring is equal to 1/2 K of x squared. So now we're just going to plug in our values. So that's going to be 1/2 times 500 newtons over meters. And you're going to multiply that by the x distance, which is 0.050 meters squared. And now entering that into a calculator, you get 0.5 times 500 times 0.0025. And this is going to equal to 0.625 joules. But rounding this to significant figures, this is basically 0.62 joules. So we're going to box this because this is the answer that was on the key. So yeah. Let's move on to question 5. A spring has a rest length of 1.30 meters. When a 20 kilogram mass is hung on it, it stretches to 3.60 meters. What is the spring constant? So again, for this, we're going to have to do a little bit of manipulation with L initial, and also we're going to use the spring constant. We're going to use the force of the spring equation. So let's write this out. 5, where you're finding the spring constant from a hanging mass. Okay, so the rest length was just L initial is equal to 1.30 meters, and the new length is going to be L is equal to 3.60 meters, and the mass M was 20 kilograms. It's 20 kilograms. So because the spring was at an extension, reading up here, yeah, the spring was when it's hung with the mass, when the 20 kilogram mass is hung on it, it's stretched to this. So that's what it is when it's like extended. So yeah, so L is going to equal to L initial plus X. But we just want X, right? So we're gonna rearrange that, and that's just gonna be L minus L initial. So now in order to get X, we just plug in those values, and the length of the string is, or the extended string is 3.60, and the initial was 1.30. So yeah, so you just get that the distance you stretch the string was 2.30 meters. And this is already in meters, so we don't have to convert that to centimeters. So, and we also know that at equilibrium, that, again, F of S is equal to 1/2 K, or 1/2, yeah, wait, that's not, oh yeah, sorry, it's just K of X. So, and also you know that at equilibrium, K of X, this is going to just equal to mg, because that's like when it's at equilibrium. So then if we just solve for K, then we can substitute that in. So we get K is equal to mg over X. And then this is going to be equal to 20, and then subbing everything in. Okay, subbing everything in, that's going to be 20 kilograms times 9.8 meters per second squared, and then, yeah, over X. And our distance was 2.30 meters. And then plugging that into your calculator, you get 196 over 2.30, and that's approximately 85 newtons. Okay, 85 newtons over meters. So yeah, that's gonna be your solution for number 5. So let's move on to number 6. Okay, number 6, a spring has rest length of 0.5 meters, and K is equal to 32 newtons over meters. If it is attached to a 30 kilogram block resting on a surface where the coefficient of static friction is 0.62, how long will the spring need to be to make the block move? So for this, we are going to be solving for number 6. We're going to be solving for the spring pulling a 30 kilogram block with friction. So to start, let's write some of the things that we have. So we know that the rest length is L initial, and then this is going to be 0.500 meters. And we also know that the spring constant K is just going to be 32 newtons over meters. And we know that the block's mass, M, is going to be 30 kilograms. And you also know that the static friction coefficient is, okay, let's add that, is equal to 0.62. Now you need to know that maximum static friction is always going to be this formula. It's always going to be F of S max is equal to the coefficient of static friction, mu s, times the normal force. And we always know that the normal force can be rewritten as mass times gravity. So then rewriting this, you just plug in the static coefficient, the coefficient of static friction, 0.62 times the mass, which is 30, times gravity, the gravitational constant, 9.8. And then plugging this into the calculator, you get approximately 182.3 newtons. Now, we know that the block starts to move when the spring force equals to this. And I'll show you what I mean. The spring force equals to, so we know from the equation Fs is equal to Kx. This is when the block starts to move, because this is the formula for it, like for Hooke's law. So we know that this is going to be Fs max. So rearranging this, we can get x is equal to Fs max divided by k, because we're solving for just x, and then we plug in everything. X divided by F of S max, we solved for it up there, was 182.3 newtons divided by our spring K, and we know that K was 32 newtons over meters. Yes, that's just 32 newtons over meters. Yeah, so this is approximately, the newtons cancels out, you get 5.70 meters. Now we want to get the final spring length. Okay, we're kind of running out of room here. Let me move this over here and this over here. So we want to solve for the final spring length. So the final spring length, that's just L. This is the extended, when it's extended fully, when it's when it's extended with the mass on it. Yeah, so that's just gonna, I guess we'll just call it final, is equal to L initial plus X, the distance that you stretched it, which is equal to 0.500 meters plus 5.70 meters. That's approximately 6.20 meters according to our key. And yeah, so that's number 6. Now let's move on to number 7. A pinball machine has K is equal to 50 newtons over meters and is compressed to 20 centimeters to shoot a 50-gram pinball. How fast can the pinball moving at the top of the machine's board if the top of the board is 30 centimeters? How fast is the pinball moving at the top of the machine's board if the top of the board is 30 centimeters higher than where the ball started? Okay, so that's a lot of variables. So let's write that down. So this is question 7. What we are looking for, we're just solving for the pinball launcher. And it's the speed at the top of board. So the spring constant K is going to equal 50 newtons over meters. Also, we know that the compression X is going to equal to 20 centimeters. And you just quickly convert this, 100 centimeters, yada yada, that's going to be 0.20 meters. Now, we also have the ball's mass, which is variable m, and that's going to be, that was given in 50 grams. And converting grams to kilograms, you have 1 kilogram over 1,000 grams, and then you just multiply that across, you get 0.050 kilograms. And we also have the height gain, which is h, and that's going to be 30 centimeters. And converting this as well, 100 centimeters, you have 100 centimeters for 1 meter, and then you get 0.30 meters. So we need to solve for I don't know if we're gonna have enough room for this. I'll just put it over here. So we're solving for initial spring energy, and the formula for initial spring energy is just let's move this over here. It's just P E spring. Potential energy of the spring is going to equal to 1/2 of kx squared, And then plugging in our values, we have 1/2 times k. K is 50 times x, which is 0.20 squared. And that's going to give you 0.5 times 50 times 0.04. That's going to be 1.0 joules. But we also know that, that's just one part of our step. We know that at the top, that energy is split into gravitational potential energy and kinetic energy. So we can write that out as PES, potential energy of the spring is going to be equal to kinetic energy plus gravitational potential energy. So we know that the potential energy of the spring is 1.0, and we know that kinetic energy, the formula for kinetic energy is 1/2 mv squared. And we know the formula for the potential energy of the gravitational potential energy is going to be mgh. So now subbing in all of our values, we have 1.0 is equal to 1/2 times 0.050 v squared plus 0.050, 9.8 times, okay, I ran out of room, let me move this over a little bit. Okay, that's 9.8 times 0.30. Now let's simplify this down. So that's going to be 1.0 is equal to 0.025 v squared plus 0.147. So rearranging this, we have 0.025 v squared, just to get v squared by itself, is going to be 1.0 minus 0.147, and this is going to be equal to 0.853. Okay, so, and then let's write that down here. Yeah, you divide both sides by this, plug that into your calculator. Yeah, so you have v squared is going to be v squared is approximately 34.1, and then you take the square root of both sides, obviously. V is, okay, is approximately 5.8 meters per second. Yay. So that is our answer for question 7. Okay, so that is it. Okay, thanks for watching.